In this video, we're going to discuss rapidly exploring random trees. And this is a great example of a sample-based planning technique. So we're going to introduce the RRT concept. We'll provide examples to introduce the RRT algorithm. We'll present a formal algorithm, and then we'll discuss smoothing of the result to get rid of some of the jagged paths that come out of it. So let's go ahead and get started. So the rapidly exploring random tree is a technique to help us create a graph as we go. So in the Verneuil graph planning technique, we created the graph and then we searched over it. And that's great if our configuration space is simple, like a 2D plane. But for when our configuration space starts to get more complex, these rapidly exploring random trees are nice because it helps us deal with what's known as the curse of dimensionality. Whereas the number of the size of our dimension, the number of dimensions we have, increases, that greatly increases the burden of planning. So over in this figure, we see an example of a particular tree searching an area. And we can see that we start off from the starting node PS, and we're trying to find a path to the ending node PE. You'll see right off the bat that this path that's produced, right, is somewhat jagged. It's not a nice straight path to the end goal, and we'll discuss how to fix that. But the other thing we'll notice is that we've created a tree, where at the very end of our tree is called a leaf, and so our endpoint is also a leaf. And each node, as you go up the graph, right, has exactly one parent. So you can only traverse in one single direction. Well, that makes our graph search really easy, because if we want to find a path from the end to the start, and we've found this tree that will connect it, then we just traverse up the tree backwards. So we follow all the parents until we get to the start. So this rapidly exploring random tree builds a nice structure, and it does so in this random sampling way. So let's discuss it a little bit more. So it's an algorithm that it does randomly but uniformly explore the search space. So uniformly meaning we're just going to sample the space using a uniform distribution. So every point has an equal probability of being sampled. And so that way we're going to be exploring in a nice uniform fashion. And it can accommodate vehicles with complicated nonlinear dynamics. And we'll go into that in future lectures, talking about how we can deal with the turning limit constraints of the vehicle within this RRT paradigm. Obstacles can be represented on a terrain map, so our obstacle map can be fairly complex, but we need to make it straightforward enough to query to detect possible collisions. RRTs can be used to generate a single feasible path or a tree with many feasible paths. So we could keep searching here and we could find multiple paths. So we could maybe go up here. Whoops, we wouldn't do that. Go through and we could find multiple possible paths. But I do want to note that without refinement, the base RRT algorithm finds the optimal path with probability 0. So that's something to keep in mind. So we can find multiple paths to the goal, and we can keep searching over it, but we actually, unless we make some changes to the base algorithm itself, we won't find the optimal path. Okay. So, and we'll discuss how to fix that. All right, so it's implemented, like we mentioned, using a tree data structure. So at the root of our tree, it's either going to be our P end or P start. Typically our P start. We could do a backward search and have the root be the end node as well. But each node correspond to a particular configuration. So each node corresponds to a particular configuration of the vehicle. So for example, if we were using our Dubin's model, we'd have a point, oh, I meant to write P, a point P and our orientation G, right? So each node in the graph corresponds to a particular configuration. Want to note that the tree is a special case of a directed graph, so we define edges, and edges here go from child to parent. So we define each of these edges, and it's directed, meaning that the edges go from the child to the parent, but they have a particular direction. So you cannot search the tree going that way. That's not allowed. Like we mentioned, the nodes correspond to physical configurations of the vehicle, and edges correspond to feasible paths. Now, an edge may constitute a series of configurations itself, or it may just denote the type of edge generator you took to get there. But either way, there's a feasible path to get from one configuration to another, where each configuration is represented as a node. And each edge has a cost associated with it. That's the Cij. So in this case, this is the cost from I to j. Because remember, if we start at the starting node, we're actually going to be going, when we execute, we're going to be going the opposite direction, even though we're building the tree going from the leaves up. Okay, so we have a cost from each node to each other node where an edge is in the graph. Okay, so to start talking about the algorithm, we're going to add in our ending node, or we'll have our ending node and our starting node, right? And we'll start with a terrain or an obstacle map. So that's how we get going. We know our starting node is PS and our ending node is PE. And each one of these obstacles, these circles, are obstacles that we don't want to get into. We're going to randomly select a configuration in the workspace. So this configuration is P, right? So we randomly select it, and we're going to try to move towards that configuration from the closest point to P that's already in the graph. So we have our graph, which, to start off with, our edge set is the empty set, right? We do not have any, or I should just say, it's the empty set. So our edge does not exist in, it is the empty set. So we don't have any edges, we have exactly a single node. So we select a new configuration and we try to drive there from our starting position, but we only go a certain distance, d. And that d is a configuration parameter that we get to choose. So we then will add v1 if this path to v1 is obstacle free, we'll then add it to our edge set. So to start here, we had our node set was just equal to the set of nodes that was just equal to PS, and our edge set was the empty set. And then after one iteration, we end up having V is equal to PS, and now we've added in this node of V1, and the edge set now consists of V1 to PS. Okay, so after one configuration, we've added that. Okay. Now we start off, right, where we just had this one single edge and the two nodes in it. And we're going to sample a new point. So now our new point is over here. And again, we're sampling typically using a uniform distribution, but as long as it's a dense sampling, that's all that matters. So we sample the configuration space, find this node P, and we try to move towards P at a distance D, right? So we're just going to move the distance D. we check this new edge, this potential edge, for collisions. So that's this step. We check for collisions, and if it's collision free, then we're going to insert V2 into the graph. So at the end of this one, now we have our vertex set is equal to, we have PS, V1, and V2. And this particular configuration, we now have two edges, and each edge points from the vertex to the starting point, vertex 2 to the starting point. That's just because we got lucky and chose the starting point twice as the nearest neighbor. So if the collisions are free, then we've added it in. So there we go. So we're going to keep doing it, and we'll generate another point. So this point now happens to be over here. Again, we try to move a distance d along that point, and we try to add another edge. So we have a choice here, right? Different variations of the algorithm will either add this red point in, or since there's a collision, it's not going to add in any points. But typically we're going to try, if we're doing the straight line, would add in that red point. But the key here is that we've now checked for collision and we've found a collision. So another thing that's different about this one is when we selected P, now V1 is the closest node in the graph. So instead of trying to extend from PS, we're extending from the closest one, which is V1. Okay. The node closest to P, we move a distance d along that line. We check the new segment for collisions. If collision free, we add it in. But in this case, there was a collision. So we didn't add in that particular branch. Okay, so we continue adding nodes and checking for collisions. So in this case now we've added nodes. We've tried to add this point P, and so we end up adding V3, and we keep exploring, and we keep trying until we find a path that's within distance of D of the end node. At this point, we could either terminate the algorithm or search for additional paths. You see, we end up making this random exploration into our configuration space and defining this graph as we go about. So if we were to add in another point, try to add another point randomly here, we would look, hey, what's our closest point to try to add to? I'm not sure which one, so let's do this one. Right? And so then we'd say, hey, this is the closest point. Let's try to go a distance d to it. And we'd add that point to our graph. Again, we could add in another point here. And this point right here would be the closest to it. So we go a distance d to that point. Right? So we just keep adding points there. We go a distance to it. Oops. A distance d to it, right? So we add that point. So we just keep randomly choosing points, and maybe we choose a point. Now we can choose a point on, if you recall earlier, we chose a point on the other side of the obstacle and we couldn't get to it. Now the closest one is that point, and that's obstacle free, right? So we go a distance d. So you see how we just keep exploring our space, randomly sampling. Okay. Awesome. So let's chat about the RRT algorithm that's presented in the book. And this is a variation of it. We come in, we have our terrain map T. This is what we use to check for collisions. We have our starting configuration, P sub S, and we have our ending configuration, P sub E. We initialize our graph, and currently our graph is, the only node in the vertex set is PS, the only edge, and there is no edge. So there we have an empty edge set. Okay, so then while the node PE, that's our end goal node, is not connected to the graph, then, so in other words, that PE is not in V, and we're going to do the following. So the code that we actually have in class adds an additional variation like we mentioned before, right? Terminate the algorithm or search for additional feasible paths. So we could say that we found exactly one path to PE, or we found multiple, right? We could choose, we're going to do 10. All right, but either way, while this is condition holds true, so we're not connected to the goal point, we're going to come in here and we generate a random configuration, P. So this is just a random configuration using some sampling, and we could actually, one variation of this is we could bias towards the goal, right? i.e., every 100 iterations, let P equal to PE. That way they'll push towards the goal. And you can see that as you decrease that number of iterations, say down to 1, we'll be trying to get to the goal every single time, and it reduces the amount of exploration. So it's a bit of a trade-off. But either way, we generate a random configuration, and typically we bias that random configuration. We find the closest configuration in our graph to P. So in this case, we look in V and find the vertex V star, which is the closest vertex to P. We're just finding the closest neighbor. Then we plan a path. So we go from, so we're going from V star to P with max distance D. So we try to plan a path, and we come up with this new node V plus, and this is either the full distance D or the last configuration before ops collision. Okay. Now we plan the path. Oh, and if there does exist a feasible path, so that's just saying, in this case, we're doing the full distance D. If there does exist a feasible path, meaning it's collision-free, and this considers our terrain map, right? So we look at our terrain map, and we try to go from V star to V plus. Then we're going to update the graph. And so the way we update the graph is this right here, this adds the vertex. And this right here adds the edge. Okay. And then we add a cost. So basically we're going to just calculate our cost as we go. So we calculate the cost as we go. Excellent. So now we enter this next if statement, and this one really should be, I'm going to put it in red, this really should be inside this if statement. Because this one checks to see if there's a feasible path from this new node V plus to PE, our end node. But we really only want to do this, right, if V plus was valid, if we could actually connect it to our graph. If we can't, then who cares, right? So we then come in here and we look to see if there's a feasible path. So we again look, we're using the same obstacle check where we're going from V plus to PE. So we're trying to go from this is the new node to the goal node. Okay, if there is a feasible path, then we'll update the graph. Now there's a couple little typos here. We don't update it as V star, it's going to be V plus. So we're going to add in P sub E as the vertex. We then add the edge from V plus to PE, and we update the cost from V plus, which is our new node, given the path length. Okay. And then we're done. So the way that it's written right here, now while the end node is not connected, if we get into here, our end node would be connected. Okay. Now, like I mentioned, we can bias towards the goal, in which case we would typically not do this portion of the algorithm. Instead, just every once in a while, we'll just try to get to the goal. And otherwise, we're just focused on exploration. Okay, excellent. And then we'll come out, once we're done with this while loop, so we've explored, we've found a path to the goal, then we find the shortest path. And this is really easy. This is just this is traverse up the tree from PE to PS. And that would give us the shortest path. So going back to, well, even here, right? So our graph search in this case is really simple, right? So we're just going to say, hey, we found our endpoint. We're going to go there. We're going to go to my parent because there's only a single possible parent in a tree. So it's always just as easy as what I'm doing here. We're just going to find that path. And that's a path from the end to the start, and we reverse the order and we go from start to the end. So that's our simple graph search. Okay. Now, one thing you notice here, and this is a great example of it, is that our path is really quite jagged. And that's common in RRT. In fact, we have no guarantee that we're going to do anything but find a path that's jagged. So instead of returning this path, which is not so nice, what we typically do is we want to smooth it out just a little bit, or remove a lot of those jagged corners. Okay, so one approach for doing this is using path smoothing. So we're going to start with the initial point, PS, and this is, we've already created a path from the start to the end, right? And then we're going to check to see how far up we can go without colliding. So to do this, we'll start at PS, and we'll look at, we already know we can get to the second node. Let's see if we can get to the third node. So we can, so we'll keep going. And we'll try to get to the fourth node. We can without any collisions with obstacles, so we try to get to the fifth node. But now we've collided with an obstacle, so we say, okay, let's bring it back and end there. And what we do is we'll just remove those two nodes and add in this edge. Okay, then starting here, we'll see, all right, we know we can get to that first one, but can we get to the second one? Yep. Can we get to the third one? Yep. Can we get to the fourth one? In this case, no. So let's end it there, and we come back here and we say we don't care about that node. We don't care about that node. Okay, and we just keep doing it. So we know we can get to that one. We could try to get to that one, but in this case, we can't go to that one because we go through an obstacle. So we go there, and we then do it one more time and get to the end. So we have this path smoothing approach that we can do after the RRT path is done. We remove a whole bunch of nodes, right, and a whole bunch of jagged edges, and we're left with a much more of a straight path. So here's the simple algorithm for doing that. Let's see. And here we initialize our path. So in this case, we add the root. We'd called it PS before, right? We initialize a pointer, I1, and we initialize a pointer to the next one. So I is the current node that we're basically trying to rewire from, or that we are evaluating the children or its descendants. Children, grandchild, and so forth. Okay, and J, then just points to the descendant that is being evaluated. Descendant being evaluated. Okay, so n is the number of nodes that is in our path. So we have this path, and the difference between here and what we were working with previously is that we no longer have the tree structure, we just have the path. Okay, so we have n nodes in our path. We get the node, so this is our sequence of nodes, and we say, hey, node I, and then we're going to try to get node j plus 1. So note that j is initialized to just I plus 1. So we're going to try to go to the child of j, not j itself. So if there exists a path from the node that we're currently using as a starting node to this w plus, if there doesn't exist one, then we're going to do stuff. If we do, so let's say that we don't go into this loop or that if statement, we're just going to keep augmenting our j. So in other words, that's what we were doing here. We're just saying, hey, oops, that was the wrong. We could get there, so we're going to keep augmenting j. And then this if statement is once we collide. So that if statement's saying, hey, once we collide, then we're going to do something. So once we collide, now we need to add a path to or a node to our new path. So we'll get the last node. So we know we can get to j. So we keep testing. We know we can get from I to j. We'll first start off as 1 to 2. Obviously, we can get there. Otherwise, the path wasn't valid to start. Then we increase j to 3, 4, 5. And it's once the j plus 1 can't be executed, then we stop with j. So we know we can get to j. We're going to add a path, add something to our smooth path. So our smooth path is going to be ws, and we're going to add our new node w. So w was the node j. We're going to update the smooth cost, so we reevaluate the path length if we need to, right? So because now our graph is going to go from ws to w. Then there's this typo in the book, right? This was a typo. We're going to let j, we're going to let I equal to j. So this is assign I the value of j. Okay, then we're going to augment j and keep going. So now we've gotten to this point where we say, hey, we can't get to this one. So now let's start working to augment j. So we keep going up. Okay, then we can't get to that one. And so we say, all right, that's going to be in our path. Okay. And there you have it. There's a fairly simple path smoothing algorithm. And there could be a whole host of other ones. This one's just a really super simple one that just goes from the start node to the start point in the path to the end point. Okay, and then we can see some results with the RRT. What you see here is that we end up crossing off like this whole section of bad points in that whole section. And we really straighten out our path, reduce the number of nodes that were in our original RRT path. Again, here's another one. The red is in our original RRT path, and that black is the smooth. So again, we've just eliminated a whole bunch of sections of the path that we didn't really need, and now we're going straight there. So again, another one. RRT, you'll see, is always going to be very jagged and going up and down and whatnot. So in this case, we can quickly get rid of large swaths of the path that are bad and connect it with stuff that looks really fairly nice. Whoops, I missed it. And straight. Okay, so there you have it. There's our first exploration into sample-based planning.